In today's lesson, we are going to learn about wind. Now, wind is air in motion, traveling between areas of different pressure. You might be wondering, what is wind? Well, to understand what makes the wind blow, we first need to understand what atmospheric pressure is. Pressure at the Earth's surface is a measure of the weight of the air pressing down to it. The greater the mass of air above us, the higher the pressure we feel, and vice versa. The importance of this is that air at the surface will want to move from high to low pressure to equalize the difference, which is what we know as wind. Now, what causes wind? So wind is caused by difference in atmospheric pressure. But why do we get these differences? It's down to the rising and sinking of air in the atmosphere. Where air is rising, we see low pressure at the Earth's surface, and where it's sinking, we see higher pressure. In fact, if it weren't for this rising and sinking motion in the atmosphere, then not only would we have no wind, but we'd also have no weather. Our next part of the lesson is, what are the different types of wind? Now, this rising and sinking of air in the atmosphere takes place both on a global scale and a local scale. Here are a few different types of wind. The first one is called small-scale winds. One of the simplest examples of a local wind is the sea breeze. On sunny days during the summer, the sun's rays heat up the ground very quickly. By contrast, the sea surface has a greater capacity to absorb the sun's rays and is more difficult to warm up. This leads to a temperature contrast between the warm land and the cooler sea. As the land heats up, it warms the air above it. The warmer air becomes less dense than surrounding cooler air and begins to rise, like bubbles in a pan of boiling water. The rising air leads to lower pressure over the land. The air over the sea remains cooler and denser, so pressure is higher than inland. So we now have a pressure difference set up, and air moves inland from the sea to try and equalize this difference. This is our sea breeze. It explains why beaches are often much cooler than inland areas on a hot sunny day. The next one is called large-scale winds. A similar process takes on a global scale. The sun's rays reach the Earth's surface in polar regions at a much more slanted angle than at equatorial regions. This sets up a temperature difference between the hot equator and the cold poles. So the heated air rises at the equator, leading to low pressure, whilst the cold air sinks above the poles, leading to high pressure. This pressure difference sets up a global wind circulation as the cold polar air tries to move southwards to replace the rising tropical air. However, this is complicated by the Earth's rotation, known as the Coriolis effect. Air that has risen over the equator moves polewards at high levels in the atmosphere, then cools and sinks at around 30 degrees latitude north and south. This leads to high pressure in the subtropics. The nearest of these features that commonly affects UK weather, is known as the Azores High. This sinking air spreads out at the Earth's surface. Some of it returns southwards towards the low pressure at the equator, known as trade winds, completing a circulation known as global circulation patterns. Another important factor that the Coriolis effect from the Earth's rotation means that air does not flow directly from high to low pressure. Instead, it is deflected to the right in the northern hemisphere. The opposite is true in the southern hemisphere. This gives us our prevailing west to southwesterly winds across the UK. Our final part of the lesson is about a question known as the jet stream. Now, what is the jet stream? Now, the jet stream is a core of strong winds around 5 to 7 miles above the Earth's surface, blowing from west to east. Now, how does it work? The jet stream flows high overhead and causes changes in the wind and pressure at that level. This affects things near the surface, such as areas of high and low pressure, and therefore helps to shape the weather we see. Sometimes, like in a fast-moving river, the jet stream's movement is very straight and smooth. However, its movement can buckle and loop like a river's meander. This will slow things up, making areas of low pressure move less predictably. The jet stream can also change the strength of an area of low pressure. It acts a bit like a vacuum cleaner, sucking air out of the top and causing it to become more intense, lowering the pressure system. The lower the pressure within a system, generally the stronger the wind and more the stormy result. On the other hand, a slower, more buckled jet stream can cause areas of higher pressure to take charge, while typically bring less stormy weather, light winds and dry skies. Now what does it cause? Now Earth is split into two hemispheres, and air is constantly moving around to spread heat and energy from the equator to the poles. Three large groups or cells in each hemisphere help to circulate this air within the lowest part of the atmosphere, the troposphere. Therefore, the jet stream exists largely because of a difference in heat, which in the northern hemisphere means cold air on the northern side of the jet stream and warm air to the south. The seasons also affect the position of the jet stream. In winter, there are more of a temperature difference between the equator and poles, so the jet stream is stronger and flows over the UK. This is why we tend to see wetter weather. The reverse is true in summer, where there tends to be smaller temperature difference. The position of the jet stream typically ends up to the north of the UK, and we see calmer, drier weather. Now, how does it affect flights? Met Office meteorologists work in only one of two centres in the world that produce weather charts for global aviation. They detail the location, height and strength of the forecast jet streams and the turbulence associated with them. Although the position of height and jet stream changes, it essentially moves around at a similar level to that of transatlantic aircraft. If you were to fly along the flow of the jet stream, it would be quicker and save fuel. However, if you arrive too early, you'll just end up circling and waiting to land. If the jet stream is weak, then this can cause delays, and if you're flying against the flow, then it'll be expensive on fuel and make you late. Flight planning is, therefore, quite a skill. Jet streams can be rather bumpy as well, especially where the wind changes its speed or when the stream isn't straight. This churns up the air like changes in a river's flow. So turbulence is another often unwelcome aspect of air travel. From a technical perspective, flying on the side of the jet stream where there is cold makes the aircraft's engines operate and burn fuel more efficiently. That's it for today's lesson. See you tomorrow or another day for the next one. Bye!